Okay guys, so let's practice on the exceptions with the half-filled and completely filled electronic orbitals. So as example we can use iron. Iron has 26 protons. Again you will do 2 s's, 2 ps's and 1 d will be enough. So what you will find after you finish with the electronic configuration that you have 2 electrons on the last force shell. So let's fill our diagram. We need to find how many electrons we have on the last energy level and how many electrons we have on the d orbital. So before you will move to the 3d orbital, you will finish with the s orbital of the fourth energy level. And after, higher in energy, will be d orbital of the third energy level. So on the last shell, here you will have 2 electrons. However, d orbital will not be completely filled. There will be only 6 electrons. So moving to the ions of the iron. Iron represent 2 oxidation states, +2 and +3. If iron will represent oxidation state +2, you will expect that iron will lose 2 electrons. And the question is from which orbital iron will donate these 2 electrons. According to the rule, iron will donate electrons from the last energy level. And here you will observe that the last energy level will be 4s2. So electron will be donated from the s orbital. And d orbital on the third energy level will stay at with the same number of the electrons. However, even if iron got rid of the electrons from the last energy level, here you will observe 6 electrons on the d orbital of the third energy level. These 6 electrons create kind of instability because all of the boxes, all the orbitals half filled, while one of them will be completely filled. This creates kind of tension between the electrons and require higher energy in order to save 6 electrons on the 3d orbital. That's why you will observe the second oxidation state of the iron +3, where iron will lose not 2 but 3 electrons. It's the same as in the first iron. 2 electrons will be donated from the last fourth energy level, and 1 additive electron will be donated from the 3d orbital. And now you will find that all 5 orientations in the d orbital will be half-filled. And stability associated with the half-filled shell arises from the fact that electrons in the same subshell have the same spin, and therefore they maximize their separation from each other within that subshell. This is a half-filled shell stability. The next example will be copper. Copper has 29 electrons. So again you will do the same, 2 s's, 2 ps's and 1 dp will be enough. So if you will finish with the electronic configuration, you will find that there are 2 electrons on the last fourth orbital and 9 electrons on the third d orbital. So let's fill our diagram in order to make it clear. And here you will find that fourth energy level filled with the s orbital and the third energy level filled with the 3d orbital. And here it's important just to stabilize d orbital, because d orbital contains 5 orientations and higher tension, higher energy required in order to hold this electron. 4s orbital will act as the donor of electron just to stabilize d orbital on the third energy level. So expected electronic configuration will be 4s2 3d9. However, in order just to stabilize our orbitals and the electrons, you will do 4s1 3d10 by donating 1 electron to the 3d orbital. So the stability associated with a completely filled shell is due to the fact that all available orbitals within the shell or subshell are filled and the electron-electron repulsion is minimized. Okay, so the last example with molybdenum that has 42 electrons. You can put pause and do by yourself in order to check how well did you get the idea of the half-filled and completely filled shells.